Bismillahirrahmanirrahim. This is Sanaullah. Today I am going to describe the hardware implementation of 16-bit replicatory adder and Lookahead. To understand them, first I will discuss the basic concept. Since we know that one of the basic functionality of CPU, which is central processing unit of our desktop PCs, is to perform arithmetic operations of different kind. For these types of operation, there is a dedicated unit. We often call it ALU or arithmetic logic unit. So in this project, we will discuss the hardware implementation of its subparts of arithmetic logic unit or ALU. We have already studied that how can we add 2-bit numbers. Now we will be discussing what kind of circuit is required for implementing these processes in hardware. So more specifically, we will be discussing the development of replicatory adder and Verilog adder in hardware. Since we know that one of the most basic adder is the addition operation of two single-bit variables, say x and y. If we have to add 2 bits numbers, we will have multiple type of results. Say if both of the inputs are equal to 0, the outcome will be 0. If any one of the input is equal to 1, the result will be equal to 1. And if both of the inputs are equal to 1, the output will be equal to 1, 0, which is binary equivalent of 2. Since we are dealing with the arithmetic, so here plus sign is representing the addition operation, not the OR operation. It's basically the a sign of additions, or we will say arithmetic operation of addition. We also know that if we have to add 2 single bits, our result could be n plus 1 bit. So in order to represent result accurately, we have to represent it in 2 bit, just like this one. If we add 1 plus 1, our result will be binary equivalent of 2, for which we require 2 bits. Next process is the same. That if the digits are more than single bit, say 2 binary numbers, which is representing 3-bit number. Now, what we do, we first solve we will first solve or add the first column. Then we see if any carry is generated, that it will transfer to the next column, and we will perform addition to that column. After that, we will move to the next column. So in this way, in the same way, we will try to implement or design the hardware which could implement the basic addition operations in ALU, as we have discussed before. Since we have already discussed, the most common or simple of the adder is the half adder. In the half adder, we have 2 single bit input lines. We represent them as, say, x and y. As I have discussed in the last slide, the result of these 2 bits could be represented in the form of 2 outputs. One is sum and other one is carry. So there are 2 numbers, 2-bit numbers, has the two input X and Y, while half adder has the output sum and carry, which is here represented as capital S and capital C. So this is the main block diagram of the half adder system. Now we will design the hardware system. If you see the truth table for this one, it is very easy and most familiar. If you have two inputs X and Y, then you will be getting 2-bit result, sum and carry. When both of the inputs are equal to 0, we will get this sum is equal to 0 and carry will also be equal to 0. When any one of them are equal to 1, then it will generate sum equal to 1 and carry will remain 0. When both of them are equal to 1, then we will have sum equal to 0 and carry will be transferred to the next column. So to accurately represent the process, we have to represent in 2-bit output. So we have represent in the form of sum and carry. Now if we represent this whole process or say design a hardware, we will see this truth table. Because if you see this truth table here, for some part the output of the sum resemble the output of the exclusive OR of bits. So for calculating the sum, it is equal to exclusive OR of X and Y. We can also represent in the AND and OR operation of the 2-bit like this one. And if we want to implement the circuit of the carry, then you can see that carry circuit resemble the simple AND gate operation, in which when both of the inputs are equal to 1, then it will generate result equal to 1. Otherwise, it will be equal to 0. So from this, you can also see that it is very simple. Where carry is generated, as the AND operation of input, which sum is represent the exclusive OR of the two input. Now this is the gate level of logic circuit of half adder, which can be designed with AND OR or AND and exclusive OR gates. Now this is the gate level or logic circuit of half adder, which can be designed with AND or exclusive OR gates. For the half adder case, we have been seen that half adder is used to represent addition of 2-bit. We have a 1 bit number and then we calculate sum and carry. But if you remember the whole process of adding n-bit number, we know that we have to follow a column-wise approach, in which we will move from right to left, starting from least significant bit to most significant bit, and we solve the addition process and transfer it if carry is generated to the next column. So when we are adding two numbers, say in the form of column, we always have to adjust another input, which is the carry in input, because after the first column there will always be a carry that would be transferring from right to left, from column to column. So considering that extra bit, we need to represent an extra input in our system, which is generally represented as C in, carry in, or Z, or by any other variable. So full adder is an extension of half adders, where we are now dealing with the 3 inputs instead of 2. Now because we have a 3 input system, so first thing is required is to draw truth table for it. So we just draw a truth table according to the three inputs X, Y and Z. And we will be calculating again the carry and the sum term. The process will remain same because when we are adding or summing the 3 bits, we have a single one in input. It will correspond bits. Whenever we have a single one in the inputs, it will correspond to a sum of 1. When we have two ones in the input here, that would be correspond to sum equal to 0 and carry equal to 1. While if we have 3 ones in the input, just like this, we will have sum equal to 1 and also carry equal to 1. So in this case, this way we solve 3 input addition process, and result is achieved in the form of sum and carry. So if we try to minimize the expression of sum and carry, what we do is to follow the K-map technique. First we use sum as the system output and put the 1 in the K-map according to the one we have. So for all these minterms, we will put 1 here. And when we try to minimize the minterm, we can see that there is no any adjacent square here. So we cannot follow further minimize this term. So we will just all these minterms here. We will just put all these minterms here just like this. And for the carry term, what we can do is we write all the ones here, which are M3, M5, M7 and M6. Then we see that how we can combine them to represent the minimized expression. For the minimized expression, we take two adjacent square like this. So this will result in expression. So this is carry and this is the sum circuit expression. After rewriting the set Boolean expression, we design 2 half adder hairs. And this, the first dotted line represent the first half adder, while the dotted line represent dotted line represents second half adder. And you can see that this is the third input. First we perform the half adder operation for 2-bit and we get the result here. This result is fed into the input of the other half adder, and next input for that half adder is Z variable. This will give us final sum as XOR of these inputs. Just sum here. For carry, we AND XY inputs and output of the first order of adder with Z term, and OR them to get carry here. Now we are going to design cascading model of full adders, also known as ripple carry adder. You see that here we have 4-bit numbers, 4-bit for A and 4-bit for B, and a 1-bit carry in. So we have a total of say 9-bit here. So if we want to perform addition of 9 bits, what we need to do is to calculate 2 power 9 entries, this one, while which is equal to 512. So this is not possible with traditional method, as we need 512 entries, and then we have to check all the values. And if number is increasing, if our number of bits are increasing, it will become more complex. So we have designed an efficient strategy for hardware so that we can easily implement n-bit adders. So to solve this issue, we follow a cascading approach of different full adders like these. First we consider the carry in is 0, and these are the first bit of 2 number. This will give sum and carry out. When first carry is generated, then the next operation will be performed. on this A1 and B1 and will generate sum 1 and C2. Similarly, for all the other adders, the same process will be applied, and in final it will generate carry out. Now we are going to discuss the concept of carry propagation. This was the circuit we discussed in previous slide. We use this circuit to represent the addition of 3-bit numbers, say x, y and z. All of them are 1 bit, and result is represented in the form of sum and carry. Now let's consider the worst case scenario, that carry is generated in the all columns. Assume that for the first case, when carry is generated after first cycle, because the A0 and B0 are available, similarly A1 and B1, A2 and B2 and A3 and B3 are also available at the time of addition, but this full adder cannot generate its result till C1 is calculated accurately. So it has to wait till C1 is generated. Then full adder 2 will generate sum. Similarly, for next full adder, result will not be generated before C2 is available. For this full adder, is also same for C3. It means all these full adders have to wait for their carry term. This full adder for C1, this for C2 and this for C3. Only then they can calculate their result. This process seems to be quite simple, but in terms of implementation, you have to design a circuit as fast as possible. Because this full adder functionality is dependent on previous full adder, similarly for this and this. Let's now consider this implementation of this full adder. We assume that each full adder here is implemented in this form, which involves 2 half adder. Let's represent this circuit as first level, this is the second level, and this became third level. So for each full adder, you have to pass through all these 3 levels. Just assume that each gate has a 1 unit delay. So it means that result would be computed after say 3 units of time. Say if it is 1 millisecond, then after 3 millisecond correct result could be generated. Similarly, if we move to the next full adder, again we will have to wait for 3 milliseconds. Similarly for third level here, and for the 3 seconds for here and 3 for here. Let's say some of the operation could be performed in parallel, because A0, B0, A1, B1, A2, B2 and A3, B3 are all already available. So because this first half adder needs only 2 bits, so for all these full adders, first level will be computed or performed. So for all this one and this one. From the second, what we have to do is that because for second level implementation of each full adder, it has to wait for Cin term, as it depends on this. So after first level, every full adder needs 2 level more delay. So for carry to be generated from input to output, we may need about 2 unit delay from this part to this. Similarly, when we are here, then from here to here, we again require to wait for 2 level delay, 1 level here and 1 level here. Similarly for 2 level here, and same for last one, which also require 2 unit delay. So for the whole of this circuit, for carry only, say we require 2k cross 4 is equal to 8 gate level delay. We have assumed that when first level is performed, all the inputs are available. So It means that the total delay for calculating sum would be 8 plus 1 unit delay. So in today's world, we require a faster system, but it is quite slow. So in order to reduce this delay, we need to design a mechanism which can reduce our carry propagation delay. This is the circuit of normal full adder. What we do, instead of SI and CI plus 1, what we do here for the sum and carry term, we add two bit intermediate variables, two intermediate variables in the system. The first one is PI and this is known as propagation, and the second one, this is known as GI generation. PI term here is called carry propagation gate term, and GI term here is called carry generation term. So we are having here AI, BI and CI, where I is the bit number. Say for first A0 here and B0 here, similarly S1 is sum 0 and CI plus 1 is the carry in for next full adder. So if we write the equation of these terms, they are very simple, because this is just the XOR, exclusive OR concept. So we can easily write it here like this. Next one is N1, which is representing the generation term here. Finally, output of the full adder is represented as SI, which is exclusive OR operation of propagation and carry in from the previous. Similarly, the next carry is here represented as CI plus 1. This is basically OR of the operation, and this one which is represented here is GI plus PI into CI. So this is the carry term. Similarly, by using simple math, all these carries equation is calculated here. In all these equation, if you note that the only carry involved is C0, which is nothing but Cin, which means it will only depend on input Cin. In order to understand the reduced delay, let's look at this logic diagram. This is a two-level diagram. This is the first level and this is the second level. This is an additional circuitry we need in order to reduce delay. So if we put this circuit in a box and calculate delay, it will only need 4 unit delay instead of 9 unit as in ripple carry adder. So this is the whole concept of my project. I will also analyze this on hardware in my next video, in which we will analyze our circuits, our delays, and difference between the ripple carry propagation delay and carry lookahead delay through on NEXYS4 DDR. Thanks for watching.